No, but I thought if I want to present something that is meaningful, I should do like what people do in AI. So you start by showing images, and then at the end you have some proofs that maybe no one will read, no one will write. Am I right? So that's what I decided to do. So I'll show you images. At least can summarize some of what I've been working on. And then I go fast on some recent result that I'll ask question. I'll ask you about the equation, whether people know the equation. Then, if people know the equation, then it may be relevant. Few things about that. But I'll show you mostly. I'll start by showing images. Yeah. So let me start by mentioning some of the kind of works I've been interested in. So I mostly work on mathematical analysis of fluid mechanics, right? So it's so you can think about it that the boundary between math and physics, because you have to use mathematical tools to analyze fluid equations. One of the first question is, and I think the word stability comes a lot, and we heard it like in previous talks, like the word stability is very important. Like even if you have very simple flows, even the simplest kind of flows, from the end of the 19th century, people were interested in question of stability of simple flows, and there are still a lot of open questions here. Then there are questions about long-time dynamic. We try to understand what happens when t goes to infinity. There are questions like transition between a laminar flow and a turbulent flow. Question about taking limits. One of the limit is implicit limit. That what happens if you think the viscosity of your fluid is very small, and then you try to study that limit. There are many other limits. Mach number, the Mach number. What does it mean to look at Mach number go to zero, so on? Like that's the incompressible limit. There are many questions about describing singularity. These are more recent kind of question. The boundary layer separation. So who knows what is boundary layer separation? No one. No one has an idea about separation, even though like this is something relevant for instance, airplane or any flight in general. And then, for me, more recently, trying to get applications of fluid ideas to other fields, including AI. Like trying to understand this, but for instance, these days I'm interested, for instance, in crowd dynamic. So you can ask yourself, how can we study crowd as a fluid? And the answer is yes. Like we have now different kind of models that are used, and one can think about the crowd as an intelligent fluid. So how people decide, especially if you have, let's say, people exiting a stadium or like huge gatherings. And then there are other kind of models when there is a panic situation. So then people will act differently. So there are a lot of questions in terms of the modeling. There are other things related also, like for instance, all what we see flocking of birds or school of fish, like when we see fish or birds. It's different than when you see humans walking together. Like when you see humans, birds or fish is nicer when you see her. I mean, there are an interesting question why that happens, but at the end, I mean, it seems as if fish or birds are more intelligent because you see more order when they go as a group. Those are really interesting kind of things that one can think about, traffic flow and so on. So these are kind of problems that one can address with some of the mathematics. I'll try to show you. So I try to show you pictures, right? Because otherwise, and then I show some equations at the end. So pictures. When I talk with, for instance, stability of simple flows, one thing that can come to mind is the stability of a vortex. So, what makes a vortex stable? Right. So there is something like you go to the equation and you see that there are. These are structures that can be stable and that can survive for days. And that is what is behind like seeing like hurricanes or tornadoes. The reason these things, we see them and they can see them for a few days and they move and so on. It's because there is some intrinsic stability of these objects. These are, of course, very important for weather prediction. I mean, I like okay, also has to do, so one can extrapolate this kind of ideas also to sandstorms or things like that. Who knows what is this?
Thunderstorm? Thunderstorm?
So it's on Jupiter.
Yeah, but it's a storm like in the atmosphere.
Vortex.
Yeah, so it's what?
It's a vortex or tourbillon. No,
Yeah, but this is a vortex where on Jupiter, right?
Yeah.
But I mean, who knows the red spot? That's what we call the red spot of Jupiter. Like any picture of Jupiter, you will see this kind of things on the surface of Jupiter. So it is like a hurricane or a tornado on the surface of Jupiter, but which has been there for centuries, right? So since people started really observing Jupiter, they realized that there is this. So I mean, if in our thinking, it's as if there is a hurricane on Earth that has been there for centuries. So of course, having this kind of things on the surface of Jupiter for that long, it means that there's something that makes it stable.
Yeah, we know it is moving. It is.
Yeah. So I mean, of course, okay. I don't want to go through all this because I mean, describing the object. I mean, one can read about it, but since people started observing it. Some century ago, it was much bigger than the size of it nowadays. So the size of it, like people observed it at some point, it was this size. I think I mean, okay, I have this number from maybe old. Now it is much smaller, but it may be oscillating also. So we don't know, right? So it's not even clear what are the right equation that are linked. So, but I think it is a very interesting kind of question to understand. So the next kind of problems I always am interested in is so-called transition between laminar and turbulent flow. So this is usually what we think about it as laminar flow, like some nice flow, versus what you see here, what usually we think about as turbulent flow. So it turns out that mathematically we understand laminar flow because they are simple. But we also understand, usually we understand turbulent flows because we use different models where you average things and they work. Usually the transition area, that's where sometimes we need more work, because normally transition areas, we try to understand how the instability starts. So usually you start with something laminar, then there is some instability that appears. At the beginning of the instability, there are a lot of works nowadays where we try to understand this. But then usually when you get a little bit before you transition to turbulent, usually we are lacking understanding. Really, the transition between the beginning of the instability and the kind of turbulent kind of behavior, right? So it's a little bit counterintuitive to think that here, well, of course, usually here people come with averaging kind of models, not necessarily justified mathematically, but they are used. There are many models for turbulent flows that people use, and they agree well with experiments without necessarily having a deep mathematical justification behind them. Okay, this is a picture. I mean, it's not a very clear picture, but I mean, just to explain, one thing is really here, this is like a flow where there are areas where it is laminar, then there are areas where it becomes turbulent. So it goes from laminar to turbulent, from laminar to turbulent. Yeah, here it's slightly more clear, but these are kind of things that we don't understand. They are hard to understand. How you transition between laminar, turbulent, laminar, turbulent. Okay, the math that I'll talk about is more related to this. So, so this is, let's say, the model for the wing of an airplane. Okay, so normally you have a flow that comes. There is a flow that comes below. There is a flow that goes above. Usually there is a lift that usually due to the fact that we have a higher pressure here than here. This is due to Bernoulli law. It tells you that the pressure here will be higher, so that will give a lift force. That makes the airplane go up. And usually when designing the wing of an airplane, what you want to maximize this, and you want to minimize the so-called drag force. And the drag force has to do with this turbulence here. Behind that, then increase the drag force. What I've explained later, like the math, is trying to understand something about the stability of the flow here after separation. So this is the point that we call separation point. And okay, maybe that's more the math part. This is pictures coming from sometimes what we call one of the most famous experiments in fluid mechanics. This is an experiment that goes back to Reynolds, 1887, to the end of the 19th century, where he discovered the so-called now Reynolds number. And here you can see by changing the Reynolds number, you can go from a flow that here normally is laminar to a flow that starts laminar but then starts becoming turbulent to something that goes more turbulent. So how how we can transition between these different kind of behaviors. This is a thing that I did work on this phenomenon. This is a phenomenon that we call now implicit damping and it is related to mixing. So, but mixing by a flow. So, I mean, you can think that if you have a flow, depending on the property of your fluid flow, it can help you mix. Nowadays, there are many industrial applications, especially in food processing. Like in food processing, they want to get ways of mixing, right? So you have to see, there are even now kind of what we call active swimmer that one can put in the flow to help mix it. So if you, this is like a flow like this. So this is what we call a shear flow. It's a flow that goes this way. But you see here it goes faster, slower, and then here it's backward. So if you start with some perturbation, if you start with something here, with some, let's say, some tracer, something that has some color, as time goes, your flow will make it look like this. I'm taking the periodic geometry. So if you go, you go back, right? But you see, particle here will go faster than you are in the middle, and that's how you can mix. And then if you add diffusion, so this is here without diffusion. Without diffusion, here we talk about implicit damping, how you can mix without diffusion. But if you add diffusion, turns out that this kind of phenomenon enhances diffusion. So there are now all literature on so-called enhanced dissipation. Any kind of idea like in our daily life, I think we use this. That if you put sugar in your coffee, like you can put sugar in the coffee and wait for a few hours, the sugar will diffuse, right? But usually that's not what you do, like you mix. So the mixing, what the mixing does, it enhances the diffusion, right? So that's one of the daily life. I mean, usually sometimes I put a picture of milk also. The coffee. Okay. So now I'll go to the second part. So this is usually in the appendix. This is the appendix part where who knows what is Navier-Stokes equation? If no one knows, then yes. Okay.
I remember a bit, but I haven't worked with it for one.
Written master course.
Euler equation. So okay, so here the physical setup, and maybe I'll go fast to just show you. There are a few other pictures that I'll show you, and then at least I can tell you what is one of the problem about stability that we were interested in here. Okay, so Navier-Stokes is a fluid equation where we have viscosity. And then there is another model, Euler equation, where we put the viscosity to zero. Now, formally, one can say, okay, if the viscosity is small, I can neglect this term, so Navier-Stokes will look like Euler. And this is mathematically rigorous if you are away from the boundary. If you are away from boundaries, this is completely rigorous. However, when you are at the boundary, if you have a boundary, this becomes, this is wrong. And it has to do with the famous paradox, the so-called D'Alembert paradox. D'Alembert proved rigorously, and that's why flight is possible. If it was true that when viscosity is zero, we go from here to here, then object cannot fly, right? So D'Alembert, what he proved, it's not a very difficult proof. He proved that if we assume that the viscosity is very small, if one takes the limit, viscosity goes to zero. Then there is no drag. Like the paradox comes from the fact that if you assume that there is a continuous limit, if we assume that there is a continuous limit, when viscosity goes to zero, the drag should go to zero. But that's not what we observe. Even when we are dealing with very small viscosity, there is always a drag. And that's due to the fact that actually the way we explain it is that it's really at the level of the boundary conditions. For a fluid that is viscous, the fluid there's no slip boundary condition, meaning particles which are on the surface will stay on the surface, will stick to the surface. Whereas for Euler, we say we have slip boundary conditions, so particle can slip. So usually that's how the profile goes. Like for Euler, the flow will not be necessarily attached, whereas for Navier-Stokes, the flow the velocity will be zero. Okay. So Prandtl, 1904, this was the International Congress of Mathematics at Heidelberg, Germany. He proposed the idea of a boundary layer, which is nowadays, this is what is, I guess, anyone dealing with flying objects will have to be talking about boundary layers to explain that the way we can go from the viscous model to the implicit model, we have to put there should be a very tiny boundary layer, a very tiny layer around the object where you say viscous effects are important, and that is usually modeled by the Prandtl system. So then, mathematically, there are two kinds of questions, two kinds of big important questions. So there is a question related to solving this boundary layer system. And then there are problems that we call them stability. I like the word stability always. It's really to prove rigorously that your original system, which is the Navier-Stokes system, which is the fluid with viscosity, is well approached by the Euler plus Prandtl. That's kind of, these are two kinds of problems that there's a big literature on both of them.
So you mean you mean Prandtl converges to Euler, right?
No.
Which one converges in Navier-Stokes?
Yeah. Navier-Stokes, this is the guy which is Navier-Stokes. You write it as the Euler plus a correction. Okay. So this is Navier-Stokes. You write it as Euler plus a correction. This together in that tiny boundary layer solves Prandtl. And so that's what Prandtl proposed. Nowadays, usually I sometimes show an ODE. If I had the board, I can show you like this. Nowadays, this is really in the spirit of what we call asymptotic expansions. Right? If you take an equation, even a simple ODE, you put a small parameter, you will try to write the equation, you make expansion based on that small parameters. And you can also rescale your variable. That's really a rescaling in the variable, because here you say that it will depend on this variable. So it means that this boundary layer correction is concentrated or varies at the scale square root of the viscosity. So it's really in a very tiny area close to the boundary. So this is how the Prandtl system looks like. This is how the Prandtl system looks like. I will just look at these two terms, this and this. So Martin, you were talking about diffusion, right? So heat equation. So it turns out here, there is a heat equation. Even though this problem is a stationary problem, I didn't put time, but there is some sort of heat behavior, meaning that one will think about this as a time-like variable. This is a space variable. These two terms together, you think about them as ux minus uyy. So it is like a diffusion in x. So we think about this when we look at the steady Prandtl system. Okay. The first one who did work on this is Olenik, 1960s. Like, she proposed way of solving this problem. But okay, maybe we'll go. Yeah, let me not go on to, these are references about the Prandtl, how we solve Prandtl, how we prove the stability of Prandtl, how we can, so there are very well-known instability. Okay, so now the Prandtl system, as I wrote it here, has this term, which is so-called this is coming from the Euler we have on top. Well, one thing I should mention that this kind of heat equation way of thinking works as long as U is positive. Right? As long as U is positive, if this is positive, you can think that there is a time is going this way, so it's x plays the role of time, so it's really like a heat equation. However, that's not always the case. So sometimes the U will try to become negative, can become negative at few places. And that's what I'm trying to explain. So before I go to there, we usually distinguish two categories, either favorable pressure or adverse pressure. So either that pressure term coming from the Euler you have on top will help you stay positive, or it acts against you, try to make you negative, try to separate your boundary layer. So again, here, just look at this. You see, this term is positive. Minus the xp is positive. And you are solving ux equals something positive. You are solving ux equals something positive. U is positive. It pushes you to stay positive. But more or less clear, right? Whereas if this term is negative, this term is negative, so you are solving ux equals something negative. So it's pushing you to become negative, right? Well, it's, from this point of view, it's quite simple to see it. And it turns out that's really something that Prandtl from 1904, he observed that there may be a term like that that can push you to become negative. So in the good situation, there are what we call self-similar solutions. So I like to mention this because I'm sure people who deal with the heat equation, they are used to this kind of scaling. This is like the long-time dynamic, the long-time behavior of the heat equation. This is like the generalization of the Gaussian. So if you think about the heat equation, diffusion, usually if you have a diffusion, you think that the long-time dynamic is that you look like a Gaussian, right? In some rescale variable. It's the same here for Prandtl. This is again in the case of favorable pressure, you will look like some function of y divided by square root of x. I think x is like time, right? That's the same as y divided by square root of t. Right? But instead of a Gaussian, we have a slightly more complicated profile. That's what, like slightly more non-linear. Okay. Now, this is now in the case of an adverse pressure, we get to a point here where we say the boundary layer separates, meaning that the pressure is pushing like this. So it's your profile, instead of staying positive, here it separates, and then here it becomes reversed. Okay. So then you have a reversed flow. And I'd like to make now the connection with what you were talking about, Matt. Like you go like this, and then you want to go back, right? So here you see, like here your flow is going this direction, but here your flow tries to go the other way around. So there may be some ideas to learn from the this is usually like the picture of that, of the boundary layer separation. Usually after the separation, there is a region that, I mean, in this picture, it becomes turbulent very fast, the flow behind the separation. But usually, if we are in a small Reynolds number, you can have a region here where you can still see a laminar flow with a reversed flow. And we go fast on this. So here, what I'm trying to explain a little bit is how we deal with the flow here after we have separation. Again, like you start with a profile, you go here. Here this becomes tangent first, and then you start separating. Your flow go back. Okay, so mathematically, how should one try to understand this problem? So we try to understand this problem by saying, here we have U which is positive, the flow is positive. Here we have a flow which is negative. I'm just going to look at this in a strip, right? So I'm going just to look at it in a strip here, right? I don't want to, going through this point, that's very hard. Trying to understand exactly what happened at this point, that's hard. But I can try to look at it in some script. That's so basically you look at the strip, and the way we want to think about it is that here the flow is going this way, here the flow is going this way. So normally I have to impose an initial condition here, and I impose an initial condition here in the trajectory. Yeah, I mean, this goes like mathematically into a category of so-called quasi-linear mixed free boundary type problem. So let's not worry too much about that. The good thing is that there are self-similar solutions that one can solve by ODE techniques. So there are exact solutions that do the reversed flow. So this is important mathematically, so that I'm not really talking about an empty set. So maybe, because you see, like physically, it's not even clear that we can solve here, and experiments show that the flow can stay, we can see as something laminar, but then it becomes turbulent very fast. So So the good thing is there is a family of solutions. So there is a family. And Stewart-John is proved rigorously. It's an ODE. So it's a hard ODE. So it's not
Simple linear.
what?
It's not a simple linear ODE.
Yeah. I think if anyone did the class prepare, this can be like very hard exam problem. I propose this to some of them. I think even they can have an exam like those 6-hour exam can be. You can have one of those 6-hour exam on just on like before. Okay, shooting method and a lot of stuff. So so then mathematically, the kind of question we are interested in is really the stability of this object, right? So we like, as I said, like one of the first things I mentioned at the very beginning, one of the things we are always interested in is stability, even of simple flow. Here, it's not a very simple flow like these FS profiles. They are not simple, I mean, because they are not very explicit. They are constructed by going through some ODE, not easy, but in a sense, we can take that FS profile and try to prove its stability. So what does that mean? If I go try to show you the picture, I start with the FS profile that is constructed by some ODE. And by the way, which is physical. That profile is what is observed physically. Yeah, maybe I should have mentioned that. The beta here is related to the angle. So you have a flow, and then you put an angle like so and depending the beta you see there has to do with the angle of your flow. So if you have a flow that comes, it hits an angle, then there is a reversed flow. There is a reverse flow because the flow that you get when you hit an angle is one of these FS profiles. So it's really also something very visible that we can see. So then the idea is to perturb this, prove that this is a stable vector. So that's really what we do. We start with this FS profile, then we make a perturbation here. So we perturb the data here, we perturb the data here, and then we prove rigorously that we keep a solution close from the solution we started with. So that's really how we usually prove stability. Stability means that you take your solution, you take your solution, you perturb it, you perturb the data, and you prove that you have a solution close. Which usually means that this is something you can see in nature. Like, because if you have a solution that the moment you perturb it, it disappears, it means that it is unstable, right? Okay, maybe I should stop here because I mean I can go and do some of the proof, but I think that's really the end of the episode.
If you want, you can still have some.
Are you still? I don't want to. I can go through something from the proof. Okay, it's fine. 5 more minutes.
Yeah.
Okay. Okay. So some ingredients in the proof. Anyone knows the Airy functions? Airy function
with a Y.
Yeah, the ODE with the Y. Yeah. So we'll see something. Yeah, so there will be some ODEs coming, like in trying to represent the solution. Okay. So here I have to impose the data. Okay, so there is a good transformation. Good and knows, this is something that we see a lot now these days in PDEs. You try to find the right quantity on which you impose your data. I'll skip trying to explain why we work with this. But here we are in a category of problems which are, even in PDEs, they are not very classical because of this feature that here you are forward parabolic. So here you expect to see a forward heat equation. Here you are expecting to see a backward heat equation. But the toy model will be something like this: y dxu minus dy square u equals 0. This is a linear equation, meaning that when y is positive, it is forward heat. When y is negative, it is backward heat. Right? So it's very simple. It's really, this is y equals 0. On top, it is forward heat. On the bottom, it is backward heat. Okay. That's, however, in our situation, it's not linear. It is quasi-linear. Instead of having y here, I have u. Instead of a y, I have u. So it's more like u dxu minus dy square equals 0. Right? So, and this put us in a category of what we call free boundary problems, because I don't know exactly when I perturb, when I make a perturbation, the curve where u vanishes is part of the problem. I don't know where u will vanish. So part of the problem is to find the new curve on which u vanishes. So the good thing is that we have some toolbox in PDEs. We have techniques that we call modulation techniques, which this. Okay, let me show you this. I think this may be an interesting kind of picture. Modulation techniques, at least in this problem, allow us to go from something where we call it free boundary, meaning the curve here, I don't know what it is, to something where it is fixed boundary. It is just a change of coordinate. I call lambda of x, I mentioned it already. I said lambda of x is the blue line, is where my perturbed solution vanishes. I still don't know it, but I'm going to construct it. So, but then I make a change of coordinate. I introduce z equal y divided by the curve on which u vanishes, right? So in the y variable, u vanishes here. This is the curve lambda of x. In the z variable, when I divide by that, the z variable, it will vanish on z equal 1, right? So that's a way of transforming the problem into a problem where it's become as if it is a linear problem. Of course, when you do this, I mean, it's just a change of coordinate. The difficulty that you had will be hidden somewhere else, right? Not like there's no free lunch. It's not because you make this change of coordinate, everything is solved. I mean, like the problem, you see it somewhere else. And actually, one of the, when we rewrite the equation in this coordinate system, we have to remember that we had the free boundary here. So the mu of s is this free boundary, and it turns out, yeah, that term comes in the equation. And okay, I mean, the equation we have is an equation like this. W bar is the guy that changes sign, but we have a term like this. One has to work to absorb it, to understand it, but I want to skip that. I want now to show you where the area equation comes. After doing all those reduction, the mu point, taking care of it, then we end up with a problem exactly like this. So you see, instead of u, now it became z. Capital Z is small z minus 1. So now when z equals 0, that's where I change from forward heat to backward heat. And this is we did a transparency. So we get this equation. So again, here, forward heat equation, backward heat equation. So how can one analyze a problem like this? So it turns out, I mean, people who are used to the heat equation usually want to need the boundary condition, right? So in a sense, here I have forward heat, backward heat, but I don't have a boundary condition here. I put the data here. I put the data here, but what is my data on the interface, right? So this is where there is an idea, which is not that difficult to understand, but okay, not right, making all the mathematics and the calculation that where they will have these area functions appearing. But the idea is that you say, okay, I'm solving the equation everywhere, so I need continuity of the functions. So here we are going to use something that we usually call Dirichlet to Neumann. Anyone heard this word? Dirichlet to Neumann kind of operator. Okay, so Dirichlet to Neumann operator means I start, let's say, I assume that I impose a data here. I call it gamma 1. Now, if I impose a data gamma 1 here, then I can solve my PDE. Now I have an equation, I solve it. I can solve it here. Then my omega is continuous, right? Because the limit I have from the top and the limit I have from the bottom are the same. But then I want also the continuity of the normal derivative. So I take a normal derivative. That's what we usually relate it to the Neumann. If I take the normal derivative from the top, the normal derivative from the bottom, there's no reason why they are continuous. Because the normal derivative from here is solved by solving the problem here. The normal derivative here is come from solving the problem here. So no reason why they agree. But if I require that they agree, the hope is that the requirement that they agree will fix gamma 1 for me, right? So you see the idea is that I start with something I don't know, gamma 1. I say, okay, let me assume that there is a gamma 1. I solve on the top, I solve on the bottom. Then I take the normal derivative from the top, the normal derivative from the bottom. I require that they coincide. And this is a little bit of work using the area function. This I can explain. The area function idea I can explain. So you see this equation. If one takes Fourier transform in S, of course now S normally is in a bounded domain, but you extend thing. You can extend thing, and then you can take Fourier in S. So if you do Fourier in S, then you get it becomes IC. I mean, people used to area equation usually the area equation usually is dz square omega minus z omega. But if you add IC, more or less the same, but it becomes complex. So it's like complex area equation. It can be solved. It's the same, but just if you replace real numbers by complex numbers, it works exactly the same. I mean, you have to be working in the complex plane, but this is a very nice ODE. We have the area functions that solve it and so on. So you can solve it. And you can solve, as I said, from the top, from the bottom, you can get exactly an expansion in terms of the gamma 1. From the top, from the bottom. You require that they are equal. You use some ODE ideas of Wronskian and so on, and then you end up with an equation that fixes your gamma 1, some fractional Laplacian. Anyone saw fractional Laplacians before? Fractional heat, yeah, like fractional, yeah. So you get exactly some fractional Laplacian on gamma 1, and that fixes your gamma 1, right? So that's how you are able to fix your gamma 1. So in a sense, that's the model you get. You get some Laplace to the 1/6 of gamma 1 is coming from some data. This is something we call some hidden electricity in the model that really allow us to get this guy in terms of the data. And that gives you the stability I was mentioning. So if instead of getting here a nice operator, you get something that has a big kernel, or if you are not able to find gamma 1, maybe you get something unstable. But the fact that you are able to fix this in terms of the data, so if my data here is small, then my gamma 1 will be small, and then I can solve it. I can get something small, so I can control everything. So that's really the idea of, again, of stability that one can prove here. Okay, so then there is a little bit more math. Turns out there is a very interesting, from physics point of view, understanding the flow here. That was very, very popular problem in the 60s, the 70s. Mathematically, we still are lacking some theory. So,
thank you very much. Can take questions.
Yeah, so you were speaking a bit about self-similarity. So I don't know if this self-similarities has some connection with the self-similarity we saw in the fractal dimensional fractal geometry as a whole.
Yeah, it's the same.
It's the same thing.
It's the same. So usually when we talk about self-similarity, it's really an idea of reducing the dimension.
Yeah.
So you have an equation in two variables, x and y, right? Imposing self-similarity means that I'm looking for a solution that instead of being a function of two variables, x and y, if you see it came twice. The idea of self-similarity came twice. It came here. It came first when I talked about glaciers. Yeah, when I talked about glaciers. So glaciers, this is really exactly like the heat equation. The heat equation is an equation, let's say, in quantity heat equation. So you have two variables, time and space, y and time. And you say, okay, I'm looking for a solution which is self-similar. Then it becomes an equation with one variable. You plug it in, and you get the Gaussian. The Gaussian comes as the profile for a self-similar solution of the heat equation. We do exactly the same thing here. This was done by Iglesias, a student of Prandtl, 1900. Slightly more complicated object finds. So instead of finding F to be the Gaussian, he gets a more complicated thing. But it's exactly like you do the self-similar solution of the heat equation. It came here. It comes also when we try to find this self-similar profile, but with reversed flow. A self-similar profile with reversed flow. These are these profiles. But instead of saying y divided by square root of x, you have to put the power, the different power. And you plug this into the equation, and then you get this ODE. That was solved by Stewart. But it's a hard ODE. Like it's not like when you do the heat equation, you get the Gaussian. Like getting the Gaussian for the heat equation, that's something you give to undergrad students. They can do it. This is much harder.
So you have solved the Prandtl equation of 1904, or the first conjecture that you gave at the beginning is now completely solved or not?
No, okay, I mean there are many parts that we understand. Yeah, there are many parts that we understand about the Prandtl.
Under some conditions.
Yeah. So, but you see, the Prandtl came after some simplifications. So and I think if I go back to the real questions about Prandtl, but what I talked about today is really related to Prandtl. I didn't talk about Navier-Stokes. Like when
you assume that you have this boundary layer, but that is a strong assumption.
Exactly. But then usually whenever now you prove something on Prandtl, you have to go back to Navier-Stokes and try to prove the same picture. Those are harder kind of questions. So that's related to the last picture I showed at the end, where you try, after you prove something here about Prandtl, you need to prove that your Navier-Stokes, the original model, really behave like Prandtl. That's usually harder.
But in the reverse,
yeah, especially because of the reverse. In this area, in this region, we understand that we can prove that the Navier-Stokes is well approached by Prandtl. Here, that will be harder, but then here it's even there are problems in terms of modeling and so on, which are quite understood at the physics level. So there are models, but mathematically we are lacking theories. Okay. I hope it made sense for
yeah. Thank you very much.
Thank you very much, Nader, for this very interesting talk. I'm not expecting that, but maybe a curiosity from the computational side. Could you comment about how, for example, solving this kind of equations is challenging, perhaps in potentially high-dimensional setting?
Okay, so that's actually a very good question. I mean, I'm personally more on the theory side, but clearly it's important, and actually we just hired like a postdoc doing CFD, like computational fluid dynamic, and I'm really learning a lot from him in terms of also like the physics. Because one thing I mean, maybe it's related. Here I showed you something about the steady Navier-Stokes. I said the steady Navier-Stokes looks like this Prandtl kind of profile. But then, and then we can talk about the stability in that sense. But now there is another kind of stability, which is the dynamical stability, right? Will we see this profile in nature. So to see the profile in nature, it has to be dynamically stable, meaning that when you don't see other kind of instability dynamically. And then talking with this guy and also with someone doing experiment, you learn that, and people doing CFD, they know these numbers immediately. They tell you, depending on the geometry you are in, so whether your geometry is flat or curved, depending on whether you work in 2-dimension or 3-dimension, there are different Reynolds numbers. Reynolds numbers, this is really a dimensional parameter that related to the viscosity. So there is the Reynolds number comes, and depending on how large is the Reynolds number, it's stable or unstable. So, and actually that goes well with what I said, like those pictures, we see this or we don't see it, meaning that if the Reynolds number stays small, meaning that the viscosity is large enough, you can expect to see this kind of pictures that I was showing, like the reversed flow. However, if the Reynolds number becomes larger and larger, and in the flat case, it's like 10 to the 5. I think that it's really something we can see. If you are in a round geometry, it's maybe 100 or 160. So it's harder to see those things. But in flat geometry, it's like 10 to the 5. So really you have to go very small viscosity so that it becomes unstable. And then they can describe for you what kind of instability. Usually there are different instabilities. They can be 2-dimensional or 3-dimensional instabilities. But you see, that's more related to the dynamical problem.
And to talk about this question of stability, I'm curious to know if people who are doing that in machine learning, I think people like Martin, in fact, in my understanding, what they are trying to do is they take images, for example, and they try to diffuse some stuff, and they assume that at the end they will end up with a Gaussian kind of Gaussian noise. And the idea of the algorithm then to reconstruct from the Gaussian the original data. So maybe I don't know if it's really a question. So my curiosity is this notion of assuming a Gaussian noise, would it be related to more theoretical questions about this Gaussian stability at the end, which from what you explained, it is related to these kind of numbers?
Maybe.
Yeah, maybe I can definitely say one thing about it, which is that there's a strong assumption in diffusion models. I mean, usually people from machine learning are used to think of a machine learning model like as simply inference of something. But with diffusion models, you really have to decouple what you think about the approximation of the score function and this differential equation that is controlling the whole sampling procedure. And there's a huge assumption in there, which is, as when I gave the intuition in my talk, which is if you run long enough, if you diffuse long enough this equation, it will be indistinguishable to run the Gaussian noise. But that is like taking like a capital T to the infinity. You never actually do that. You actually always approach a Gaussian without actually really reaching that Gaussian, meaning that you have a first boundary problem in there, because when you're going to come back, you're actually going to not come back to this almost Gaussian distribution, but with a pure Gaussian distribution. So it's like you made a shift in there. And since you made a shift in there, actually you can prove that the seemingly equivalent like ODE or reverse SDE that were supposed to describe your regenerative process don't become unequal because of this boundary problem. it would only be equal if you actually reach pure Gaussian noise analytically, but you never do. And this is not something that you really reflect at the level of how you learn the score function. Because the score function is just you take a grid and then you learn this in this grid, or maybe you use some way of allowing the neural network to like allow time, like a continuous time time point, like the time values to as inputs. But this first assumption is a big one. And Anderson's time reversal formula actually has to do with, I mean, the way you prove it is by going to the partial differential equation setup and jointly solving what are called the Kolmogorov forward and backward equations simultaneously. And somehow, I mean, I see it as an analogy of what you have in here, that simultaneously there is a forward evolution and a backward evolution. And the whole mystery is what is happening in this in between. So even before getting into discretization, you can optimize your everything and then discretize, of course, for computational purposes. But already in the analytical sense, there is already that problem to be solved. You see.
But okay, maybe not really necessarily related to your question, but my understanding in terms of, like, for instance, the usage of machine learning in solving equation like this, I think now we see more and more people trying to do numerics using machine learning, and so in a sense, you want your computer to learn how to solve faster, right? So we are seeing, I'm seeing some papers on that. So and being used also, like, to solve Navier-Stokes, for instance. I think these are interesting questions, even I guess from the math point of view, also how to justify why it works and so on.
Okay. Does anyone else have a question? No? Okay, well, thank you very much for this very high-end